All right, 4025 MAA Mechanics tutorial 11. This is about principle of work and energy, kinetic energy, potential energy, impulse and momentum. So let's start with exercise level 1. You have the spring in this toy gun with an unstretched length of 100 millimeters. And it is compressed and locked in the position shown. So we have that at instant 1, the spring is compressed 50 millimeters. So it's 100 millimeters unstretched, and it's 50 millimeters in this position 1. When the trigger is pulled, the spring unstretches 12.5 millimeters, and the 20-gram balls moves along the barrel. Determine the speed of the ball when it leaves the gun, neglect friction. Now we know that this is, we can call this instant 1 in our case, and we have instant 2 for which let's call this instant 1. This here, when the ball is here, and when the ball is here, we have instant number 2. So what we want to determine the speed of the ball when it leaves the gun. So we're going to use the principle of work and energy. I have put here the formula sheet that you will have available in during the exam. So we can have so we have already a description here of the work of a constant force, the work of weight, the work of a spring, and some other definitions, including the principle of work and energy itself, very important. So we're going to start by doing the free body diagram of the body that we are interested in, which in this case is the ball. And as you know, on the ball is acting the weight force, so the weight of the ball, mg, a reaction force, normal force from the barrel. There's also a spring force, which is, of course, propelling this forward. And I think that's it. There is no friction. Yes, says neglect friction. So there's no friction. Therefore, these are the only 3 forces acting on the ball. And they are both acting at instant 1 and at instant 2. So these are the same, exactly the same. So let's see the displacement. The displacement is in this direction. So this is the displacement S is happening along this direction here. Therefore, we know that the only forces that do work, well, the only force that is working is the force in the direction of the displacement. This force is not working. This force is not working because they are perpendicular to the displacement. You can see a work of a constant force, F, the force itself, times the displacement times the cosine of the angle between the two. Of course, this is theta is 90 degrees for N and S, and for mg and S. Therefore, the cosine of 90 degrees is 0. You can also look at this as the work of a weight force. It works in the same way since there is no vertical drop. So the vertical position at instant 2 is exactly the same as the vertical position at instant 1. You have that U12 for the work done by this weight force in particular is 0, which is exactly what we said earlier. So let's apply the principle of work energy itself. So this is the principle of work energy. It's T1 plus the sum of all the work done between instants 1 and 2 equals the kinetic energy at instant 2. Remember, the kinetic energy is defined as half the mass times the velocity squared. In this case, we have only translations. Remember, this is the general kinetic energy is this. But of course, we have that omega in this case is 0. So we don't experience rotation. All right, so let's start. Let's put everything in formulae. So we have that. So the only one, this sum contains a single element. So we have that half the mass of the ball times the velocity of the ball at instant 1 squared, plus, and we are looking at this now, we're looking at the work of a spring. So the work of a spring is minus, not plus, minus half the stiffness of the spring, which is given here, times the stretch at instant 2 squared minus the stretch at instant 1 squared. Okay, this is exactly the same as this, equals half m v2 squared, where v2 is the velocity at instant 2, which is exactly our unknown. So this is what we want to find. This is a single equation, and it also has a single unknown, because what you have is that everything here is given. The only things are we need to find what is the stretch at instant 2 and the stretch at instant 1. So let's find S2 and S1. S1 is 100 minus 50 millimeters. How do I know? Because it says here, so this is the unstretched length of the spring is 100. At instant 1, the spring is stretched 50, it's 50 millimeters long. So that means that the unstretched minus the stretch, so sorry, the unstretched initial position minus the final position gives you 50 millimeters of stretch. In this case, is compression. For S2, it says that when the trigger is pulled, the spring unstretches 12.5 millimeters. So that means that we add 50, so it's 100 minus 50 plus 12.5 millimeters. So it's 100 unstretched. Then we compress 50, and then when the ball is here, the spring has unstretched 12.5 millimeters. So we need to add 12.5 millimeters to this, and this results into 62.5 millimeters. And now we have all we need. So we can just say, we also know that V1 is 0, because the ball starts at rest. Therefore, we can just rearrange, where we can also take this and this out of the equation, because it's 1/2. So we can rearrange everything to be minus k over m times S2 squared minus S1 squared under square root. So V2 equals the square root of this number. So of course it looks negative, but it is not, because what we have in the end is that this number is greater than this number. Okay, so if you do this calculation, you should get 10.5 meters per second. Of course, it's plus or minus 10.5 meters per second, but we only take the correct one, the positive one. As you can see, this is very simple. Let me check if I've done everything correctly. Or if this means that, does this mean the spring unstretches 12.5? Does this mean that this, because this looks to me that 50, this is 62.5 minus squared, minus 50 squared is a positive number. So this is negative, so this is impossible. So I believe that this already gives you the unstretched length of the spring. So what I'm saying is that after when the ball is here, when the ball is here, this spring has unstretches 12.5. So it should be something like this. So in this case, we have 12.5 squared minus 50 squared is a negative number, and we get this. Okay. So let's do now exercise level 2. So we have a collar with a mass of 20 kilograms and resting on a smooth rod. This collar here has a mass of 20 kilograms resting on a smooth rod. There are 2 springs attached to this and the ends to this and the ends of the rod. Each spring has an uncompressed length of 1 meter. So it's showing this position here as the rest position of the system. And if the collar is displaced 0.5 meters towards the right and released from rest, what is its velocity at this instant here when it goes back? So we have that now instant 1 is this instant here when the collar is in this position here, and instant 2 is this one where the collar returns, springs back into position. So let's do, let's apply the principle of work and energy, but first let's do the free body diagram, of course, of the collar. So this is the collar, and of course it feels 2 forces. Let's say if it's moved on that position, then of course both spring 1 and spring 2. So let's call this K2 and this K1. They are different they are springs of different stiffness, as you can see. Then of course there is the weight of this. And there is the normal force from the rod itself, because it's a collar. Okay, so the only forces, of course, that are working are these ones, because the displacement S is horizontal. Therefore, these forces are not working. This is just the same thing. We just have to do this very carefully. So for the principle of work and energy, T1 plus U12 of spring 1 plus U12 of spring 2, because that's what we have, equals T2. Now this gives half mv1 squared plus, sorry, minus half k1, the final stretch squared minus the initial stretch squared, minus k2, the final stretch squared minus the initial stretch squared, equals T2 is half mv2 squared. So we know that this starts from rest, so this is 0. It starts from rest. And we need to calculate the stretches, so the final stretch and the initial stretch. Now we know that this final stretch, since it's exactly in this position here that we said is the rest position, so these are 1 meter long, 1 meter uncompressed. And since this is 1 meter and 1 meter, we can say there is no stretch and no stretch for either spring when in position 2. But when in position 1, this stretch is 0.5 meters. And this is for spring 1. So for spring 1, this is a positive stretch. let's do something plus 0.5 meters squared. And for this spring, it's a negative stretch, so it's a compression. But of course, as you can see, since it's squared, it doesn't matter if it's a stretch or a compression, because either number is squared. V2, again, is the only thing that we need to find. So we have one equation, only one equation, and so we need a single unknown. This half can go away, because it's common to every term. So we are left with minus K1 S1 squared minus K2 S1 squared equals MV2 squared. So finally, I can say that this is, that means that V2 is the square root of K1 plus K2 divided by M S1 squared with a negative value. No, this S1, S2, and these are the same value. Oh, this is that. This is a positive and positive, because this is minus 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 minus, so we end up with a positive thing. Okay, so make sure that you know what you're doing. So this is exactly what it is. And this should be 1.37 meters per second. Okay, now let's do exercise level 3. For level 3, we have this ball with a mass of ½ kilo, suspended from a rubber band and a stretched length of 1 meter and a stiffness of 50 newtons per meter. If the support at A, this one, to which the rubber band is attached, is 2 meters from the floor, determine the greatest speed the ball can have at A, so let's say the initial speed. So this is 1, so that it does not touch the floor when it reaches the lowest point P. So we want, let's say, this, when the ball reaches here, barely, so it must be just enough that it doesn't touch, that it reaches the ground without bouncing off it. We want to know what is V1, basically. So what is V1 such as the ball can reach this point too? Let's do the free body diagram of the ball. Forces acting on it are mg and, of course, Fk. This is the spring force from the rubber band. Well, now the displacement is going in this direction. Thus, it means that this means that both forces are working. Both forces are working. This one is doing positive work. This is doing negative work. All right, so let's apply the principle of work and energy using the principle of work and energy. We have that half. Let's do this properly. So T1 plus the U of the weight between 1 and 2 plus the U of the spring force 1 and 2 equals T2. That's it. There is no friction, no resistance. And so recall that the U work 1, 2 is minus mg times y2 minus y1. And U of the spring 1, 2 is minus half k, the stretching 2 squared minus the stretching 1 squared. And we have the idea. So let's explicitate this. We have half mv1 squared. Now v1 is our unknown. This is what we want to find. Minus mg. Now let's look at y2 minus y1. Let's say that this is the y-axis. And let's say that the y-axis starts at 0 here. So this is my origin. So y1 is 2 meters and y2 is 0 meters. In this case, we have y2 minus y1, for which y2 is 0 meters and y1 is 2 meters. And as you can see, the work, as I said, is positive because y2 is 0, y1 is 2 meters, but there's a negative sign. So this becomes a positive value because we know that this is going in this direction. And so the work done by the weight force is positive, as I was saying. All right, so let's go further on. We have minus half K. K is the stiffness of the cable that we have 50 newtons per meter. Divided, times S2 squared minus S1 squared. S2 is the final stretch. Now, the original length of the cable was 1 meter. So the cable is unstretched when it reaches this position here. The cable is unstretched. So that means that at position 1, at position 2, the stretch is this one. At position 2, the stretch is this 1 meter of stretch. So this one is 1 squared. And in S1, of course, we know that this cable only has a stretching potential. When it's compressed, it doesn't push the ball because that's what rubber bands do. So we can say there is no stretch. Let me put this. We can say there is no stretch at instant 1. And finally, this results into mv2 squared. We know that this ball must touch the ground and bound and not rebound from the ground, but make sure that it doesn't touch the ground. So that means that the speed at this point must be 0 because it's turning back. It's the point, the instant in time for which it's turning back. So that means that v2 is also 0. This one is 0. And it's not this that is 0, it's this velocity 2. But finally, we can just rearrange the equation again. Now we can't get rid of 1/2 because there is no 1/2 here. So let's multiply everything times 2. We have that v1. So solving this, we have that v1 is the square root of mg y1, because this is 0, so I will not, and it's 2mg y1 plus k s2 squared. There you go. This should be the final result. And this should be also 7.79 meters per second. Quite simple. Again, it's all a matter of making sure that you know how many forces are acting on this and which forces are working, and also explicitate what is the work of these forces over the two instants. Let's do exercise level 4. So if the coefficient of kinetic friction between the 100 kilogram crate and the plane is 25%, what is the compression X of the spring required to bring the crate momentarily to rest. So this is instant 1. And instant 2 is where the crate is here. This would be instant 2. So let's do the free body diagram. Let's see how many forces are acting on our crate. And we have that there is the friction. Oh, sorry, let's start with the weight force, G. Then we have the normal force, N. Then we have the friction force, FF. And of course, when it's at 2, we also have the spring force, FK. Now, the displacement is happening in this direction. And so we know that this force is a reaction force N, and it's never working, of course, because it's always perpendicular to the direction of motion. Isn't it divided by M, the last part of the question? Yes, you're right. Thank you. Thank you. So this goes away, and this is divided by M. Cheers. Yes, because I forgot to divide everything by M as well. Thank you about that. I was saying here, we have 4 forces, 1, 2, 3, 4. This one is not working because it's perpendicular to S. This one is negative work against S. This is negative work against S. And this one, well, this one is peculiar because it has some component along the direction of motion, of course, and some component perpendicular to the direction of motion. So I can say that mg is working with us, so it's working, does positive work, but not the entirety of mg does positive work because some part of it doesn't work. Okay, so let's, in this case, we need to find ff. Remember, ff is also equal to mu k times n, so we need to find n first. So let's take the x, y axis, and let's take this is the y axis, this is the x axis. And I'm going to say that n, so for the y direction, n minus mg cosine of theta equals 0. Why mg cosine of theta? Because you know that this one is the angle theta of interest. Let's do it like this. Let me draw it like this so it's clear. This is mg, and mg has a component like this and a component like this. This angle here is theta. So this one here is is mg cosine theta, which is exactly what we're looking at. And this one here is mg sine theta. So of course now theta is 45 degrees, so they have the same magnitude, but it doesn't matter. This works for every theta anyway. So we can say that n, in the end, we get that n is mg cosine theta, whatever it is. And so now we can go and use the principle of work energy. So we have T1 plus, let's see how many forces are working. This one is working, this one is working, this one is working. So let's say that the U12 of the weight plus U12 of the spring plus U12 of the friction equals T2 final. So this is half mv1 squared plus, sorry, negative, because it's the work of the weight force, mg times y2 minus y1. let me write it down first, minus half k of S2 squared minus S1 squared. And this one, we need to be very careful about this because this is the friction force. We know that the friction force is a constant force. So for the work of a constant force, it's always equal to the force times the cosine of theta times the displacement S2 minus S1. Okay, so times whatever displacement it has undergone. So the displacement is, well, let's just write it down now. So it's F, so cosine of theta, we know that this theta here, well, let's not call it theta because otherwise we have, let's call this alpha, beta. And beta is this angle here, it's the angle between S and FF, which is of course 180 degrees. So beta is 180 degrees. And so that means that in our case, this is just minus, so cosine of 180 is minus 1. So it's minus the friction force times the displacement delta S. And this is equal to, half mv2 squared. Now, what do we know about these? Well, we know that the initial, the spring is unstretched and the crate is at rest. So this is 0 because crate at rest. And of course, we also know that at V2, the crate is also at rest. So this is also 0. Now we need to find y2 and y1. Well, of course, y2 is the, let's say now, y2 is the vertical direction in this case. So it's the direction the force is acting towards. So this is a different y-axis. Okay, let's call this y prime. So I'm saying this is y prime, and this is the actual y-axis. And let's say that my coordinate system starts at an origin that is this one. So I say that y2 is 0, and y1 is whatever this is. Now, y1 is this distance. Y1 is this. And so as you can see, this is the triangle so this is the triangle, and so this is exactly the distance we want. Okay, so this one here is y1, sorry, y1. So how much is that? Well, the hypotenuse is 10 plus x, and the angle is 45. So we know that y2 is 0, as we said. Y1 is, the hypotenuse is 10 plus x, where x is the stretch of the spring after this crate has bumped into it, times the this theta, so sine of theta. The final stretch of the spring is exactly x squared. This is the stretch of the spring, and the initial stretch of the spring is originally unstretched, so this is 0. FF is, of course, mu k times n. Delta S is just this, it's 10 plus x, so it's however much it has moved in that direction. So this is 10 plus x. Okay, now this becomes a bit more complicated to write, so let me write everything down. This is minus mg times minus 10 plus x sine theta minus half k x squared minus mu k mg cosine of theta, that was n times 10 plus x equals 0. Should be everything's correct. Yeah, let me rearrange this to remove the negative sign here and here. And also this, so not required anymore. This one is the final thing. Our unknown is x. Of course, we want to know how much is the stretch. And this x is the x that comes from a quadratic equation. So let's rearrange this to look like a quadratic equation. We have mg 10 sine, so 10 mg sine theta plus mg x sine theta minus half k x squared minus mu k minus 10 mu k mg cosine theta minus mu k mg x cosine theta equal to 0. And so I can just regroup. This is my x squared, this is my x, and these ones are my known terms. So I can regroup this as half k x squared, this x squared, plus mg sine theta minus mu k mg cosine theta x yes, and the last one is plus 10 mg sine theta minus 10 mu k mg cosine theta equals 0. Now this one, these are the coefficients a, b, and c. So you can just solve this to find, you can find x equals plus, sorry, b squared plus or minus square root of 4 b plus or minus b squared minus 4ac divided by 2a. Okay, the usual formula. So you have two values for x. One will be a negative value, one will be a positive value. You, of course, want the positive value. That's it. So it's not very complicated. Does it make sense? So let me call this one A. This one is B, and this one is C. Okay, now for the exercise level 5, I solved it already earlier because I didn't think there would be enough time. There is enough time, but let's go through the solution together. So we have a material hoist and the load, so this thing here, have a total mass of 800 kilograms, and the counterweight C has a mass of 150 kilograms. At a given instant, the hoist has an upward velocity of 2 meters per second and an acceleration of 1.5 meters per second. So put all the information here. Determine the power generated by the motor M, which is here, at this instant if it operates with a certain efficiency of 80%. Says epsilon here, use eta because epsilon looks like strain. I don't like that. So we do the free body diagram first of the hoist and the counterweight. Of course, if I cut here, as you can see, if I cut here, I have, this is a single strand of rope. So since all the pulleys are massless and frictionless, and the cable is inextensible, we have that this is whatever T is carried around is the same. So we have two T's, I called it T1 for the right hand side of the hoist. This is a completely different rope, so we can't say it's the same tension. I'm going to call this T2. These are the forces acting on H, including its own weight, of course, mg. And in C, well, for the counterweight itself, it's very easy to see that it's just T2, it's exactly the same as this, and its own weight, mg. So if I use the equations of motion for the hoist, this is for the hoist, this is for the hoist, and this is for the counterweight. For the hoist, I have 2T1 plus T2 minus mg equals mass times the acceleration of the hoist, the mass of the hoist times the acceleration of the hoist, which is given. And for the counterweight, we have T2 in its own, so this is its own reference frame, and this is its own reference frame. They are going in the same direction. So positive T2 minus mg equals mass times the acceleration of the counterweight. Now, of course, we need the kinematic relationship between these two, because these are free body diagrams on their own. So what we want is the relationship between these two. And we know that if since there is only a rope, if this goes up 1 meter, this goes down 1 meter. So that means that they have the same acceleration, but opposite. So an acceleration in the y direction for H is an acceleration in the negative y direction for C. And so we have that AH is minus AC, and I call it A for both of them. So I can just take this and say this is minus MA, and this is MA. So from here I find T2, which is M times G minus A. Very easy. And it's a certain value in Newton. Now that I know T2, I can put it here and just find T1, which is this piece around here. And this is another certain value in newtons. Now what's left is we want to find the power generated by the motor M at this instant if it operates with a certain efficiency. Now, the motor looks like this. So the free body diagram of the motor is not required, but it's very useful to see what forces are acting on the motor. And of course, only the tension of this cable is, well, the motor is generating the tension in this cable, basically. So this is the only thing. And we know that the power is the force generated by the motor times the velocity at which this force is moving. Now, the velocity of this cable is not the same as the velocity of the hoist. Okay, you should agree with me that this pulley here is rolling up onto this, strand of rope. So that means that the velocity profile looks like this. So this is the pulley. So we have rope on one side and rope on the other side. This point is instantaneous center of rotation because this pulley rotates around this point. This one, this velocity here is the velocity of the hoist itself, so in the middle. And so we know that the velocity here, which is the velocity of this one, it must be double as much. So it's V prime, which is the velocity of this strand of cable, is twice as much the velocity of the hoist. And so we want the force of the motor times the velocity of that strand of rope. And that gives T1 times 2VH, which is a certain amount of watts. And that's the power required from the outside but in order to overcome the friction, internal friction inside here, we need a power in that comes from this efficiency equation, of course. So the power that we need to generate is equal to the power out divided by the efficiency. So it is a larger, since eta is 0.8, so divided by a number smaller than 1, you have a number that is greater. So you have in the end that the power that you have to provide, the electrical power you need to supply the motor with, is greater than the mechanical power you will get out of it in the end. And it's greater by 20%. It's 20% greater. Okay, so this concludes the tutorial. And this is also our last tutorial. We will not have a session next week. So if you don't have any questions, I think I will stop recording. Let me stop recording first.